you.
So we can go to dinner earlier. So our next speaker, the last speaker is Dr. Yoji Koyama. He will talk about the Hawking radiation externally from super-translated horizon.
Thanks for introduction, and thank you for the organizers for giving me this opportunity to talk my recent work. This is a collaboration with Professor Johnson Chu here at NCTS. And today I'll talk about Hawking radiation as tunneling from super-translated black hole horizon. This is introduction. In the introduction, I briefly explain the so-called BMS super translations and the super translation here on black hole. BMS super translations are the asymptotic symmetries of asymptotically Minkowski spacetime. And the super translation here on black hole is recently proposed by Hawking, Perry, and Strominger. And if we consider BMS super translation in some black hole spacetime, this super translation here appear. And this is a new kind of black hole here, which may be used to distinguish black hole with the same mass, charge, and angular momentum. So this is usually black hole has only 3 kinds of hair, but they propose that the black hole has more hair. And after the introduction, I move on to our model. And our central question is whether Hawking radiation from black hole with super translation hair carry information of this super translation hair. And in this work, we consider Hawking radiation as tunneling. This picture and the concrete computation of Hawking radiation as tunneling is initiated by Parik and Wilczek in 2000. Okay. First, I'd like to explain BMS super translation. In the analysis of BMS super translation, people the so-called boundary coordinates V, R, Z, and Z bar is most frequently used. So this is a Minkowski metric in the advanced boundary coordinates. Here V is advanced time, which is given by T plus R. And this gamma AB, theta A, theta B is just a metric on the unit round sphere. Okay, and theta and AB is AB run from Z and Z bar, and Z and Z bar is just a complex coordinate on that unit to sphere, which is given in terms of a polar coordinate as this. And this is a Penrose diagram of Minkowski space. And there are some infinities, and in the analysis of BMS super translation, the so-called null infinity plays an important role. So there is a past null infinity. So, and the future null infinity, square plus and square minus. And all the radiation come from the past null infinity, and finally come out from the future null infinity. Okay. So, okay, in your work, so we work in this advanced boundary coordinate, not in this retarded boundary coordinate. Okay. So please remember this diagram. And I talk about Minkowski metric in boundary coordinate, and next I go to asymptotically Minkowski spacetime. And we work in the so-called boundary gauge. This is just a coordinate choice. And to discuss asymptotically flatness of spacetime, we have to specify asymptotically fall-off conditions at large R. And this is a typical asymptotically fall-off condition, which is discussed in the original paper of BMS super translation. Okay. And with this gauge condition and asymptotical fall-off conditions, we have the any metric can be expanded in terms of R, in terms of large R. So the symptotic expansion of asymptotically flat spacetime is given by this metric. Okay. The first line corresponds to Minkowski metric, and the second line corresponds to the correction. And all are the higher order in 1 over R. And okay. So if we forget about this, CAB and NAB, so this Minkowski spacetime plus this 2m over R term is usual black hole metric. Yeah, you are very familiar with. Okay, so then we can define BMS supertranslation. BMS supertranslation is diffeomorphism, which preserves the Bondi gauge conditions as well as the asymptotic fall-off condition for asymptotic flatness near null infinity. And this BMS supertranslation is generated by the vector field theta given by this form. This vector field satisfies this preserves this Bondi gauge and asymptotic flatness. And here the function f is given by this function is this f is a function of angular variables, and this is arbitrary function. So this means that supertranslation is parameterized by function, and there are infinitely many transformations which preserve gauge conditions and asymptotic flatness. And this BMS supertranslation is generalization of time translation to angle-dependent time translation. Okay. So then once we have BMS supertranslation, we can define the conserved charge associated with this supertranslation, QF, which is defined at not null infinity, spatial infinity, and which is given by the surface integral over the unit two sphere of the supertranslation function f times this m, which appear here. Okay. And usually the supertranslation function can be expanded in terms of spherical harmonics with arbitrary constant. Okay, so this is the supertranslation, and this is called the supertranslation charge. And then next, I'd like to briefly explain about supertranslation here. So we discussed BMS supertranslation and supertranslation charge. So then we consider, for example, Schwarzschild spacetimes with different supertranslations, which means that the black hole spacetime has ADM mass and supertranslation function, but we consider has a differently supertranslated Schwarzschild spacetime, which has a supertranslation function f tilde. So classically, so if we consider these two spacetime, classically black holes are characterized by the ADM mass and supertranslation charge. But it turns out that these two spacetime has exactly the same ADM mass and the supertranslation charge after the integration, because in the Schwarzschild spacetime, this m is just a Schwarzschild black hole mass, and which is spherically symmetric. So then after the surface integral, this gives us just a constant result, and two supertranslation charge coincide. So then these two charges which characterize the spacetime are independent of supertranslation. So then at the classical level, black holes do not carry the classical supertranslation here. So there is some other symmetry which can be interpreted as classical supertranslation here, but so today, so I will not talk about this, so then please forget about this sentence. So then let's go to semi-classical level. So quantum mechanically, black hole can evaporate. So then we can observe Hawking radiation. So then if Hawking radiation depends on supertranslation function f, the black hole with different supertranslations actually can be distinguished from each other. So then in this case, black hole have supertranslation here carried by Hawking radiation. I finished introduction, and here is a setup of our model. We consider the so-called dynamical black hole because during evaporation, so during when black hole emit Hawking radiation, black hole will be dynamical due to the back reaction of Hawking radiation. And this kind of dynamical black hole can be described simply by so-called Baija spacetime, which gives a simple model of dynamical black hole. And we study Hawking radiation as tunneling from Baija black hole with supertranslation here. It's namely supertranslated Baija black hole. Okay. So next I explain supertranslation of Baija spacetime. So this is a metric of Baija spacetime in advanced Bondi coordinate. And here capital B is defined by 1 minus 2m over r. And if this m is a function of advanced coordinate, m depends on time. But if m is constant, this metric reduces to a Schwarzschild coordinate, Schwarzschild metric. And this metric describes asymptotically Minkowski metric containing a Baija black hole. So then we do super translation to this metric. So which is given by, so this metric is just a infinitesimally super translated Baija metric. The super translation is just given by this vector field I discussed before. Okay. So then every component is shifted by a super translation, which is characterized by super translation function f. Okay. So here m prime is just a time derivative of black hole mass. So then there are some remarks. So we obtain this super translated Baija metric by simply do the diffeomorphism, but we can also reproduce the super translated Baija metric by injecting some matter energy momentum tensor which has angular dependence. Some energy momentum tensor T mu which depend on this angular dependent function f. And as I already discussed in Schwarzschild spacetime, so in this spacetime we compute ADM mass, but ADM mass is constant and does not depend on super translation. Okay. So then the third remark is that because BMS super translation is translation which preserves the asymptotical forward condition, so they usually define only near null infinity. But in this case, this super translated metric satisfies Einstein equation for arbitrary r. So then we can use this super translated metric not only near infinity but also the whole entire space-time. So then, especially near the black hole horizon. Yeah, because this is important because later we consider tunneling, Hawking radiation as tunneling, and this tunneling usually occurs near horizon. So then we need some validity of use of this metric near the black hole horizon. Okay. So next, I talk about some property of super translated Baija black hole. Our first property is horizon. So because we are considering a super translated black hole spacetime, so then we want to know first that whether there are really black holes in this spacetime. So to do this, we consider the so-called trapping horizon. So let theta plus and theta minus and theta plus be the expansion of the bunch of ingoing and outgoing radial light rays. So which is in the super translated Baija spacetime, the expansion is given by this. So this is basically if this expansion is positive, the bunch of light rays are expanding. But if this expansion is negative, the bunch of light rays are contracting. This means that gravity is strong. And okay, so then the so-called future outer marginally trapped surface is defined by these conditions. And the main condition is this theta plus equals to 0. This means that outgoing massless radiation are parallel. And this condition gives the we can solve this equals to 0 in terms of r equals to RH. Actually, this r equals to RH gives a location of horizon. And the other two conditions are satisfied very trivially, so that I don't explain. So then the horizon, the future outer trapping horizon, is given by a foliation of this future outer imaginary trapped surface. And this future outer trapping horizon, which is given by this R equals to RH, gives a local definition of super-translated Baija black hole. So then actually, the super-translated Baija spacetime include contain the black hole, even defined by this trapping horizon. So then the next property is surface gravity. Surface gravity is just gives acceleration at the horizon. So then in the we are considering non-spherical symmetric spacetime, but in the spherical symmetric spacetime there are a good definition of surface gravity, which is given by Kodama vector. But I think because of time, so maybe I cannot explain everything here. So but we can extend the good definition of surface gravity in spherical symmetric spacetime to our non-spherically symmetric super-translated spacetime. And we found that at the future outer trapping horizon, we have surface gravity which depend on super-translation. This is the point. Okay. So then finally, I talk about the Hawking radiation as tunneling from super-translated Baija black hole. So before going to the detail, I explained that Hawking radiation as tunneling. So here, please interpret this dotted line as horizon, and we consider tunneling of particle from this black hole horizon. So we consider some trajectory of positive energy particle like this. So because from the black hole, particle cannot escape. But if we consider the trajectory which moves backward in time, this kind of trajectory, the particle cross the horizon. But this kind of trajectory is classically forbidden. Okay. But in the tunneling, actually, this kind of trajectory happens. And this kind of trajectory can be interpreted in different way. So so if there is a virtual particle pair production just outside the horizon, the negative energy particle fall into the black hole. On the other hand, the positive energy particles are tunneling through the black hole horizon. Okay, so this is the origin of Hawking radiation. Okay, so then in this picture, we can derive the Hawking radiation from black hole. So how many minutes do I have? 7. Okay. Okay, so then maybe I have to skip all the detail of computation. But according to the tunneling picture, we can compute the emission rate of Hawking radiation from black hole in a very simple way. So then I just show you the result. Yeah. Okay. Basically, we compute. We solve the triangle equation in black hole spacetime with WKB ansatz, and solve the equation of motion. We have action, and the tunneling actually comes from the imaginary part of this action. This is the signal of tunneling. So then the semi-classical emission rate is given by the exponential to -2 times imaginary part of action. Okay. So then we can compute the imaginary part of the action for super-translated Baija black hole in the very simple way, and the result is given by this. Okay. And actually, this imaginary part comes from the location of horizon. Okay. This is just a location of pole of the integral. So then the resulting semi-classical emission rate is given by WKB formula, and which is given by the exponential to 2 times imaginary part of S, and which is given by this. Actually, the semi-classical emission rate depends on the supertranslation function F. And this result can be written in terms of the surface gravity, which I obtained before. So this is completely formally, this is completely the standard expression for Hawking radiation. So then this means that Hawking radiation actually depends on supertranslation. So then I skip this slide. So then this is summary. So we found that Hawking radiation from the supertranslated Voyager black hole will actually carry information of supertranslation function F. But in the static limit from this result, because the supertranslation, dependence of supertranslation is proportional to the time derivative of m. If we go to static limit, that dependence disappears. And from our result, we can say that we can distinguish black hole with different supertranslation here by Hawking radiation. Yeah. And the tunneling of massless particle occurs at the tropical horizon. And the spectrum of Hawking radiation, the semi-classical emission rate can be expressed in terms of the horizon surface gravity kappa, which can serve as a local measure of Hawking temperature. And this is there is a remaining question. All are not easy, but I'll explain everything. So maybe I should skip. Thank you very much.
Question or comment?
Does your work invoke BMS symmetry?
Yes?
And BMS symmetry is a infrared property.
Yes.
But black hole itself also contain not only the infrared property, but also more higher energy properties. How can you use BMS to describe the whole black hole?
Actually, okay, this is a long point. Yeah, in the current work, we just consider we first consider supertranslation near infinity, and we supertranslate the black hole spacetime like this. Okay. But this metric itself is a solution to the Einstein equation for all R. So this is a solution not only near the infinity, but also the solution of entire spacetime. So that we can use this metric not only near infinity, but also the interior of spacetime. Of course, there are some discussion for the extension of translation from infinity to interior of spacetime. But in the current work, so we just consider the metric, which is the actual solution to the Einstein equation for all R.
So supertranslate by their metric is kind of boundary condition?
Yes, this Voyager metric actually satisfies the asymptotical Hall of condition. So then this is asymptotically Minkowski spacetime.
And then you continue to the inside of it.
Yes.
Any more questions? If not, let's thank all the three speakers of this session, and they did a very good job to end this session earlier. Any announcement from the organizer?